Hi there, Physics 152. This is the theory video for the week 5 practicals. Let me share my screen here. All right, so this is about capacitors and capacitance. And I'm going to be going along with your night textbook, Physics for Scientists and Engineers, chapter 26. So basically, the idea here is you've got two electrodes, which are two conductors that are separated by some space, and the space in between them is insulating. So a separation of charge creates an electric potential difference, such as shuffling your feet on the carpet transfers electrons from the carpet to you, creating a potential difference between you and the other objects in the room. This potential difference can cause sparks. So, for example, here charge is separated by moving electrons from one electrode to another. The separation creates an electric field from positive to negative. So once you've got plus Q on one side and negative Q on the other side, then the electric field points from the positive to the negative. And because there's an electric field, you also have a delta V, a potential difference between those electrodes. So the separated charge has created a potential difference, even though the whole net charge of the two electrodes together is 0. So the figure shows two arbitrary electrodes charged to plus and minus Q. And there's a potential difference, delta V, which we're going to call delta VC, which is directly proportional to Q. The ratio of the charge Q to the potential difference, delta VC, is called the capacitance. C is defined as Q over delta V. For a parallel plate capacitor, there's an equation for that, epsilon naught times A, the area of either plate, divided by D, the distance between the two plates. So you're going to use that equation a lot in this week's practical. So good one to know. And so, by the way, again, from this, you've got a universal constant, epsilon naught. You've got area and distance between the plates. These are all just based on the geometry of the capacitor. So capacitance is a purely geometric property of two electrodes because it depends only on their area and their spacing. The SI unit of capacitance is called the farad. A farad is 1 coulomb per volt. The charge on the capacitor plates is directly proportional to the potential difference between the plates. So we say Q is C times V, the charge on a capacitor. So let's do a quick example. What is the capacitance of these two electrodes? So you can see they're both charged to a charge of plus and minus 4 times 10 to the minus 9 coulombs. That's a typical kind of charge. And it's doing this with a 2-volt power supply. So basically, capacitance is just Q over V. So that's 4 times 10 to the minus 9 coulombs divided by 2 volts. So 4 over 2 is just 2. 2 times 10 to the minus 9. And the SI unit is farads. And we call that a 2 nanofarads. So capacitors are important elements in electric circuits. You're going to be playing with them in labs this week. They come in a variety of shapes and sizes. These are some capacitors. The keys on most computer keyboards are capacitor switches. Pressing the key pushes two capacitor plates closer together, increasing their capacitance. So this is again from Knight. It's about the energy stored in a capacitor. And if you look at this diagram, so the idea is that you use a battery to charge up a capacitor. And in Knight, they use this, what's called a charge escalator model for a DC battery. Basically, you imagine a little charge when it goes through the battery. It's as if it's being pulled up an escalator and given some higher potential. So it goes from minus to positive. It gets a potential potential energy du, which is dq times delta v, the change in electric potential. So that little dq gains dq times delta v. Delta v is proportional to the instantaneous charge on either plate divided by the capacitance. So in order to find the energy stored in a capacitor, you have to do an integral, starting from 0 charge up to the final charge, capital Q, lowercase q dq. So q is the instantaneous charge, which starts at 0, ends up at q. You do an integral of 1 over c times q dq. You end up with a factor of 2 in the bottom, q squared over 2c. So capacitors are important elements in electric circuits because of their ability to store energy. The charge on the two plates is plus or minus q, and this charge separation establishes a potential difference. Delta V is q over c between the two electrodes. In terms of the capacitor's potential difference, the potential energy stored in the capacitor is that q squared over 2c, also 1/2 c times delta V squared. Another good equation. A capacitor can be charged slowly, but then can release the energy very quickly. So an important medical application of capacitors is called the defibrillator. A heart attack or serious injury can cause the heart to enter a state known as fibrillation, in which heart muscles are twitching randomly and are not pumping the blood properly. So what a defibrillator does is it sends a strong electric shock through the chest, which momentarily completely stops the heart, giving the cells that control the heart's rhythm a chance to restore the proper heartbeat. Okay, dielectrics. Again, you're going to need to know this for practicums this week. A figure shows a parallel plate capacitor, which is separated by a vacuum. So there's the delta V, there's the Q on either side, and distance between them. When the capacitor is fully charged to some voltage, you've got this Q is C times V. But in this section, the subscripts 0 are placed all over the place, and they refer to a vacuum-filled capacitor. I think the next slide is, so now I take those same two plates, and the next slide, I insert a new insulating material between the capacitor plates. And this could be anything. It could be a piece of wood. It could be just air, I guess, in the room. That's not a vacuum. It could be paper. You're going to use paper, I think, in labs. But an insulator in an electric field is called a dielectric. And so just slipping in a dielectric, it doesn't change the charge on the capacitor, but you'll find it does change the voltage. And this delta VC is now less than delta VC 0. And I'll tell you why. It's not totally obvious, but it's, let's see here. Okay, so you know that an insulator can be polarized. So if you place an insulator in an electric field, then it will stretch apart all of the atoms inside the material. It doesn't move them around, but it the external electric field separates the positive and negative charge in a sense that all the pluses shift a little to the left here, and all the minuses shift a little to the right. And what you end up is a central neutral region. If you look at all these, there's counterparts, and then kind of a surface of positive charge over on this side and a surface of negative charge over on this side. So if you imagine eta here, eta is 0 as being the charge divided by the area, so the surface charge density on these capacitor plates, that will set up an electric field. So Q over A, and then there's a epsilon naught on the bottom. That gives you the electric field in a vacuum. But now, when you insert a dielectric, you don't just have the negative plate and the positive plate. You now have this polarized, I guess, surface charge density eta induced. So there's an induced positive surface charge on this left side and a negative on the right side. So there's an induced electric field within the dielectric due to its charge redistribution, which is to the right here. So the electric field is one way. The induced electric field from the polarization of the dielectric is in the opposite direction. And what that does is it weakens the net electric field. So the net electric field is the superposition of that vacuum electric field coming from the plates of the parallel, the conducting plates of the capacitor. And then it's reduced by that opposite induced field that's within the dielectric. So you end up with a smaller electric field, and that leads to a smaller voltage. So we're going to define the dielectric constant is the ratio of the vacuum electric field to the actual electric field. The dielectric constant, like density or specific heat, is a property of a material. Easily polarized materials have a larger dielectric constant than materials that are not easily polarized. A vacuum has a dielectric constant of 1 exactly, because it's the electric field in a vacuum is the electric field in a vacuum, so E0 over E0. Filling a capacitor with a dielectric, turns out it increases the capacitor by a factor kappa. So this C, which is Q over delta V, is going to be Q over delta V divided by kappa. The kappa comes up on the top. So it's the capacitance, it turns out to be kappa times the vacuum capacitance. So that's what it does. And I think there's a tape. Oh, it shows here that many practical capacitors, like some of the ones you'll be using, tend to use a solid or liquid dielectric. So you've got these two plates, metal foil, and then slipped in between them is an insulating dielectric. Oh, okay. So, and last thing, all materials have a maximum electric field that they can sustain without producing a spark. At least with solids, this will happen. So, for example, if you think of lightning, that happens when the electric field is greater than 3 million volts per meter. 3 million volts per meter, just up to that, like 2 million volts per meter, you can sustain, a voltage difference, and the air is an insulator. Above 3 million, and then the air actually becomes a conductor, and that's you get a great big spark there. So a material's maximum sustainable electric field is called its dielectric strength. Yeah, so this is the last slide. It's just showing a table from your textbook of the dielectric constants of some various materials arranged from increasing dielectric strength. So air is almost like a vacuum. 1.0006 is the dielectric constant of air, so not much. But if you use Teflon or Mylar or paper, actually, this is one kind of paper. I think you're gonna measure in your lab the dielectric constant of textbook paper, which might be different. But again, it's gonna be kind of in the 2 to 4 sort of range. Glass. Water turns out to have a very high dielectric constant, and that is because what happens is that the dipoles of the water molecules will actually rotate around, and that creates this dielectric constant of 80. And then it's showing here the dielectric strength. So there's in millions of volts per meter. So air has 3 million. It's much larger. I don't think you can really create a spark in pure water. So it's a little bit more complicated, but you can see where a lot of these materials have a breakdown. It's pretty high. Okay, so that's it for your theory video. I hope you have a great week 5 in practicals. Bye for now.